Hi all. Now we can study the modeling of rotational mechanical systems. We have already studied the modeling of translational mechanical systems. Now we can study the modeling of rotational mechanical systems. Rotational mechanical systems move about a fixed axis. Here also we have to consider three basic elements. They are moment of inertia, torsional spring and dashpot, similar to translational mechanical system. Now, if a torque is applied to a rotational mechanical system, it is opposed by opposing torques due to moment of inertia, elasticity, and friction of the system. Since this applied torque and the opposing torques are in opposite directions, therefore, the algebraic sum of torques acting on the system is 0. Now we can study these three elements separately. First, we can see the moment of inertia. In translation mechanical system, mass stores kinetic energy. Similarly, in this case, the moment of inertia stores kinetic energy. This opposing torque, it is proportional to angular acceleration of the body. And this, if a torque is applied on a body having moment of inertia J, a torque is applied on a body and it has a moment of inertia of J, then this opposing torque, it is called inertia torque. It is equal to the product of this moment of inertia and the angular acceleration. So that is equal to this opposing torque. It is called inertia torque. It is equal to J into d square theta by dt square, where theta is the angular displacement, or J alpha, where alpha is the angular acceleration. Therefore, inertia torque, it is equal to the product of moment of inertia and angular acceleration. In the translational system, inertia force, it is equal to the product of mass into acceleration. In this case, in the rotational system, this opposing torque, it is equal to the product of moment of inertia and the angular acceleration. So remember this equation, opposing torque, it is called inertia torque. That's equal to J into d square theta by dt square. Now consider the second element, that is torsional spring. In translation mechanical system, spring stores potential energy. Similarly, in this system, rotational system, torsional spring stores potential energy. And now again, if a torque is applied on a torsional spring K, then it is opposed by opposite torque. Due to the elasticity of torsional spring. This opposing torque is proportional to the angular displacement. So this opposing torque, it is equal to K theta, where K is the torsional spring constant. Angular displacement, in the previous case, that is in translational system, this restoring force, it is equal to K into x, where x is displacement. Here it is equal to K into theta, where theta is the angular displacement. Now the third element, dashpot. If a torque is applied to a dashpot B, then it is opposed by an opposing torque due to rotational friction of the dashpot. This opposing torque is proportional to angular velocity, and this opposing torque is equal to B into d theta by dt, where d theta by dt is the angular velocity, theta is the angular displacement. B is the rotational frictional coefficient. There is torque voltage analogy for rotational mechanical systems similar to force voltage analogy for translational mechanical system. In this analogy, torque voltage analogy, the mathematical equations of rotational mechanical system are compared with mesh equations of the electrical system. First, consider this rotational mechanical system. The torque balanced equation is applied torque is equal to sum of all opposing torques. So T is equal to Tj plus Tb plus Tk. Three elements J, B and K. Applied torque, angular displacement, theta. So this is equal to T is equal to J into d square theta by dt square plus B into d theta by dt plus K theta. Now comparing these two equations T is equal to J into d square theta by dt square plus B into d theta by dt plus K theta, and V is equal to mesh equation. V is equal to L into d square Q by dt square plus R into dq by dt plus 1 by C Q. We will get the analogous quantities of rotational mechanical system and electrical system. So it is given in this table. Torque T, analogous value is V, voltage V, moment of inertia J, inductance L, rotational friction coefficient B, resistance R, torsional spring constant K, reciprocal of capacitance 1 by C, angular displacement theta, charge Q, angular velocity omega, current I. Next is torque current analogy. In this analogy, the mathematical equations of the rotational mechanical system are compared with the nodal equations of the electrical system. That is, T is equal to J into d square theta by dt square plus B into d theta by dt plus K theta. And nodal equation is I is equal to C into d square psi by dt square plus 1 by R d psi by dt plus 1 by L psi. We will get the analogous quantities of rotational mechanical system. So comparing J, C, torque, current, moment of inertia J, capacitance C, rotational frictional coefficient B, reciprocal of resistance, torsional spring constant K, reciprocal of inductance, angular displacement theta, magnetic flux, angular velocity omega, voltage V. So again remember this table. Remember these equations, then you will get the analogous value. Now one problem. Write the differential equations governing the mechanical system shown in figure. Let the angular displacements of J1 and J2, let it be theta 1 and theta 2 respectively. The free body diagram of J1 is shown in this figure. The opposing torques acting on J1 are marked as Tj1, Tb1 and Tk1. Tj1, Tb1 and Tk1 in opposite direction. By Newton's second law of rotational systems, rotational motion, the sum of these opposing torques is equal to applied torque. So Tj1 plus Tb1 plus Tk1 is equal to T, that is J1 d square theta 1 by dt square plus B1 d theta 1 by dt plus K1 into theta 1 minus theta 2 is equal to applied torque T. Now the free body diagram of J2 is shown in this figure. The opposing torques acting on J2 are marked as Tj2, Tb2, Tk2 and Tk1. This K1 is connected between two nodes. Therefore, the corresponding torques J2 d square theta 2 by dt square plus B2 d theta 2 by dt plus K2 theta 2 plus K1 theta 2 minus theta 1 is equal to 0. So these are the differential equations. These two mathematical representation, they are called modeling or mathematical model. Thank you.